This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I have one-handed for you today. You don't have it in your hands because we're going to pass it around. It's really the one. I'm going to have TAs pass it around during the lecture. I sent out an email on Saturday. Does anyone not get that email? Probably a handful. Oh wow, nobody. Everybody got it. That's great. Okay, you did not get the email? Okay, well, if you can, email me directly after class so I can figure out what the deal is. The reason I say that is because I just realized over the weekend, this is totally my fault, that the section room for tomorrow, Skilling 193, seats 48 people, and I'm telling everybody to go to it. So I have to figure something out there. Normally that's going to be fine because most of you will just watch it on TV and get in the habit of doing that, but tomorrow I kind of want you to go. So I'm working on one of two solutions. I'm either going to try and get a bigger room just for tomorrow for 4:15, or I'm going to get a huge room at 3:15, still have the 4:15 section, and try and push everybody to go to the earlier one if they have any flexibility. So I will make a decision as to what, based on what rooms are available to me later today, and I will send out an email, which is why I'm asking about the email. Okay? So definitely stay tuned for a CS 107 email later today. But I left you a question right there.
What's the time again?
Tuesday at 4:15 are the normal sections. I may have one. May is the operative verb there. I may have one tomorrow at 3:15, just tomorrow, to accommodate the sheer number of people I expect to show up. Okay? When I left you last time, I was doing little asterisk and ampersand tricks. Let me do another one. I have a double D that I set equal to 3.1416. And as a result, I actually get a fairly large figure in memory that's populated with pi. We'll decorate this with the D variable. And if I go ahead and I do the following, car CH is equal to asterisk car star ampersand of D. There was a little bit of confusion about this. Because of that ampersand operation right there, the actual bit pattern that resides in the 8-byte figure that we're calling D, the bit pattern is actually irrelevant. This is an expression on the address of D. It doesn't have to look inside the 8 boxes to figure out what's important here. It has to evaluate that address because that's there. It's seduced into thinking that it's actually storing the address, that it's an address of a single character. So when it dereferences this right here, it goes and it embraces that single byte right there. Whatever bit pattern happened to reside there before is now pretending to be a character for the lifetime of this statement right here. Does that make sense to people? So if this happened to be, I don't know what it is, but suppose it's this bit pattern right there. Okay, this variable called CH will get that very bit pattern, and if I go ahead and do cout less than CH less than ENDL, whatever this corresponds to gets printed to the console. Okay, that makes sense to people? Okay, let me do one more little tricky thing here. If I declare a short, oops, and I set it equal to 45, I get a 2-byte figure that has a 45 in it. It's stored in binary, but I'm just going to write 45 because it's easier to look at that. And I do this. This is where you get into a little bit of danger. Double D is equal to asterisk of double star ampersand of S. Most of what I've said prior applies here as well. This is one scenario where things are a little bit mysterious. This right here evaluates to the ampersand of S. That's the address associated with that arrow, the number associated with that arrow. And this is a brute force reinterpretation of that address. So what's going to happen is it's going to say, oh, wow, that arrow now, it never pointed to a short. It actually points to an 8-byte double. So it will go and not only include those 2 bytes right there, but the 6 bytes that follow it. Okay, whatever bit pattern happens to reside there, provided there's no memory crash, and I'll explain why that could happen in a second, as long as it gets away with it, it's going to go and embrace all 8 bytes of those 8 bytes of information there, interpret it as an 8-byte double, and then assign it to this thing called D. So if this is a 45 followed by that as a byte pattern, then D would get 45 with this as a byte pattern. And when I print that out, it's going to print out whatever number happens to be associated with that representation. Does that make sense to people? Okay. Now I could do these for days. Okay, and show you every little combination between asterisks and ampersands and double asterisks and whatnot. I want to move on and start talking about arrays and structs first, because I think you'll just get more practice there. We'll start learning some more material. There's a question right here.
Yeah, are these examples going to behave differently on a little Indian?
Certainly, yeah. They, well, as far as the bit copying is concerned, no, this ampersand right here is always the address of the lowest byte. But as far as how the ending in this has to do more with interpretation and placement of bytes relative to one another. As far as, there's these phrases in the handout that I kind of de-emphasize, but they're there, and since you're asking, I'll talk about it. Little endian. If I were to write down a 2-byte short, like that, and if I were to store the number 1 in that short, you would just say, oh, well, the 1 just goes right here, and it's preceded by 15 zeros. Does that make sense to people? Okay. That is true on about half of the systems in existence at the moment. This right here, not only is it a representation for positive 1 as a 2-byte short, it happens to be stored in what's called big endian format. And the best way to remember that, it's kind of arbitrary as to what big versus little means in this context. I just remember it as the lowest byte stores the bits that correspond to the largest contributions of magnitude. Does that make sense? Okay, and since 1 is such a small number, that's why you have all these 1s over here. On some machines, in particular the Linux machines that you're probably working on, it would store this with the bytes in the reverse order. Okay? It would actually have the 1 right there preceded by 7 zeros, followed by 8 zeros right there. And it's just when it goes and interprets it as a 2-byte short, it actually assumes that these are bits 0 through 7 and these are bits 8 through 15. Does that make sense? So if you actually were to, and you could do this if you wanted to, if you were to copy a 2-byte short from a Linux machine to a Solaris machine and just do it on a byte copy level, you wouldn't get the same numbers on different machines. Okay, you would get 1 on a big endian machine here, you get 256. I'm sorry, yeah, 256 on a little endian machine. Does that make sense to people? Okay, for the most part, you don't have to worry about endianness at all. There's one aspect in assignment 2 that happens to deal with it, but I more or less insulate you from it. Okay, just something to be sensitive to. What I want to talk about now are structs, how they work, how arrays work, how arrays of structs, structs with arrays inside all work. Given what we know already, let's kill this. Let me go ahead and declare this as a struct right here. Very simple. Struct fraction int num int denom. That right there, that's the C way. I'll assume we're in C++ for the moment. That's enough to just declare fraction standalone as a new type. If I do this fraction, let's say pi as a variable name. As a result of that, I obviously get enough memory to store a fraction. In 106B and 106X, and maybe 106A as well, you drew them as these somewhat loose rectangles around 2 boxes. Okay, I want to be a little bit more structured than that. I want to recognize that the amount of memory that's set aside for the struct fraction, not surprisingly, is 8 bytes. Okay, it's basically the sum of its parts, and it actually packs all of those bytes as tightly as possible. I'm going to draw this as 8 bytes. I'm going to emphasize the fact that it's really 4 bytes stacked on top of 4 more bytes. The address of the entire struct is always coincident with the address of the first field. So looking at this and assuming that that's a picture of one of these things, you know that this is the num field. In this case, it'll be pi.num because that's the way I declared it right there. And stacked on top of that, 4 bytes above the base address of the entire thing would be pi.denom. Okay? So when I draw that arrow right there, unless I give you some context, you don't know whether it's an int star pointing to the address of the num field, I'm sorry, storing the address of the num field, or the address of the entire struct. Okay? When I do this, not surprisingly, that places a 22 in the lower 4 bytes of the entire figure. The more technically accurate way of saying it is that it actually stores a 22 to the field that's at an offset of 0 from the base address of the entire struct. Okay? That's why a 22 gets placed there. When I do this and store a 7 somewhere, because it recognizes based on this definition, which it certainly sees before it sees this line right here, it knows that denom is stacked on top of num. Because num is a 4-byte integer, that denom is 4 bytes above the base address of the entire thing. And that's how it knows where to put the 29 zeros followed by 3 ones for the 7. Okay? If I go ahead and do this is where things get crazy. If I go ahead and do this, ampersand of pi.denom. I'll do that. You don't technically need it, but that makes it clear what you're taking the address of. I have an int star, right? Unless I do this. Okay, and now I have the address of a fraction. So what happens is just on the fly, it stops thinking about this address right there as a standalone integer, or pointing to a standalone integer, but now it has this picture all of a sudden, at the moment, that it's addressing this 8-byte picture that overlays that space right there. So when I go ahead, let me actually draw this a little bit more accurately. I go ahead and do fraction asterisk, and I do this. Num is equal to 12. The arrow comes after something that at that moment is assumed to be the address of an entire fraction struct. So the arrow travels to that struct, so there's not much traveling to do because it's already there, and then it goes inside and identifies the num field as the place that should receive the 12. Where is that num field? It is right here. Does that make sense to people? Okay, so if I go ahead and I just print out, cout less than pi.denom, behind pi.denom's back, it was changed from a 7 to a 12. Okay? If I do the same exact thing, fraction star ampersand of pi.denom arrow denom is equal to 33, it's not going to be concerned about the fact that I really don't own the space above what is truly pi.denom. The way the mechanics work takes the base address of this, oh look, it's a fraction star now, go 4 bytes beyond that to find out where the 33 belongs. It's going to smear down the 4-byte representation of 33 in this space right here. And there's no legal way to get to it and print it out, but if I did this again to the right of a cout statement, it would print out a 33. Does that make sense to people? Okay, good. Let me do one more thing. And actually, let's go on to arrays. Int array. Very different from Java. We didn't talk about arrays in CS106B and 106X as much as we will in 107. Question in the back?
Yeah, sorry, I don't know if I caught you correctly, but did you say that when you set the fraction and then ampersand p.denom, the num to 12, does that mean when you access pi.denom that it's going to be 12? And
that is correct, right. You happen to invade pi.denom space using some quirky syntax. Okay, just because you happen to know that pi.denom resides above pi.num, just because you reinterpret the address to be associated with a different data type, if you happen to operate on space that overlays the original pi.denom, then you're affecting what really is pi.denom's value.
So is there any way to access the denominator or the denom of the 4-byte representation within the 4-byte representation? How can you access that 33 without doing another fraction?
You actually can't. I'm sorry. You certainly could use this expression again to do so.
Can't access it any other
If you wanted to, I mean, this will be more clear after I do the array example. But if I wanted to, since you're asking, pi.denom fraction star Okay? Do you understand? That's the address of the top 2/3 of the drawing. What I could do is I could do something like this. That's a little sneaky. That'll be clear after I do the formal array example that I'm covering up right now. But that's effectively a dereference to go and get to the denom field. Okay? I wouldn't even have to do this necessarily. I could just do address of pi of 1.num is equal to, or print that out or something like that. Okay? I mean, this will become more clear after I talk about the array business a little bit.
Because what's at the 1 index is actually a
It
fraction.
literally is 8 bytes beyond what's at the 0 index. Okay? If you don't get that, don't worry. Well, I'll start with a simpler example right here. This right here, you know this already. It allocates 40 bytes of memory, okay, for the 10 bytes that are being set aside and are under the jurisdiction of this keyword called array. So I'm going to draw it this way and do a modulo 5. It's good enough. You know that this is the 0th index, and you assign to it using array of 0. This is array of 9. So when I go ahead and do something like this, array of 0 is equal to 44. I put a 44 there. You know this. If I do array of 9 is equal to 100, a 100 goes there. What you may not recognize is that array itself is synonymous with the address of the 0th entry. Okay, let me write that down as like a little theorem. In the context of that declaration right there, array is completely synonymous with ampersand of array of 0. Okay, that's why when you pass an array to a helper function or any function whatsoever, you're not passing the entire array, you're just identifying the location of the 0th entry, and from that you can access anything legitimately beyond it as long as you know how long the array is. Okay? If I go ahead and do this, to create some tension, 45, then obviously 0, 1, 2, 3, 4, 5, that's nothing new. If I go ahead and mess up, and I don't understand for loops, and I don't understand arrays well enough to not make this mistake yet, if I go ahead and I write down the number 1, it's consistent with the offsetting that's done relative to the base address of the entire thing. This right here assigns a 44 to the int that is 0 ints forward of the base address. Go ahead 9 quantums of integers to find out where the 100 should go. Go ahead 5. Java's a different story, but in C and C++, there's no bounds checking done at all on raw arrays, and that's exactly what this thing is right here. So when I do this, it really says, oh, well, that's interested in that address right there. This 10 is interpreted to be 10 times the size of an integer, which is 4, for a 40-byte offset from the base address right here. So it goes right there, and it leaps forward 40 bytes to the base address of what it has no choice but to assume is an integer space. So it's going to go down. Whether it causes problems or not is a different story. It'll try and place a 1 right there. Okay? If I do this, of 25 is equal to 25, and somewhere over here, a 25 is laid down. Okay? It actually even tolerates negative numbers. It's that brute force. I don't want to put 0. That's not very useful. 77. It would march back 1, 2, 3, 4 places to figure out where to place the 77. And that's how memory, as a side effect, would be updated by these bogus little statements right there. Okay? Does that make sense? Question in the back?
You can make the assignment of array 10 if it's going to do that anyway.
I'm not sure what you mean.
Well, you said in array 10, like you initialize it 10, like spaces, but what's the point of initializing it if it's just gonna do basically do what you know when you get inside of it?
That is true, actually. This right here is really just documentation for how much space is being allocated, and then you're supposed to write code. I'm not saying this is good code. I'm just saying it's code. Okay? You're supposed to write code that's consistent with the amount of space that you legally have, but this, and this just work because there's no bounds checking. It doesn't look arbitrarily far backwards to figure out whether or not it's an in-range index. So when it gets away with this and it compiles and it runs, it's just going to put a 1 where it assumes that the 11th entry would be, or the 26th entry, or the -4th entry. Okay? That makes sense? Okay. Yep.
Does declaring it at size 10 somehow protect the memory?
It doesn't in C and C++. Not at all. I mean, all it does is an instruction for that one declaration as to how many variables, more or less, how many ints to set aside space for. But once you do that, like, the length of the array is, the length of the memory figure, it's not exposed to you, so there's no way to recover it. That's why you always pass around the length with a raw array in C and C++. Okay, you used vectors more than you did raw arrays in 106B, but we're going to be more C programmers than C++ programmers for the next few weeks, so we don't have vectors because we don't have classes and we don't have templates. Okay, so we have to actually take this approach right here. Okay, yep.
So you use the address of pi and you accessed it as an array there. Is it going to know that the size of each element is a fraction?
Yep, it uses the data typing of whatever pi is right there. And because ampersand of pi is an int star, it knows that if you just all of a sudden start treating it as the base address of an array, even if it is really only an array of length 1, it's going to deal with a default offset of 8, because that's how many bytes are in a fraction. Okay? So this will become a little bit more clear after I put a few more little theorems over there. Okay? When you do this right here, let's say this way, array of k, where k is an arbitrary integer. The address of that thing is completely synonymous, and you did not see this all that much, if at all, in 106. It is synonymous with this right here. Okay, so the first line isn't array so much as it is array plus 0 on the left-hand side. Okay? This right here, given that example, array is of type int star. There's no storage for array. It's not like the address or the base address of the array is stored anywhere that you can manipulate. But this is of type int star. If this is assumed to be an integer, which it is in this example, then you're not doing normal arithmetic here. You're doing what's called pointer arithmetic. And it knows that you're not going to be dealing with arbitrary bytes inside an array. You're only supposed to be concerned with the boundaries that separate the space where one int ends and another one begins. So whenever this is understood to be a pointer right here, this number isn't added verbatim. It is automatically scaled by the size of the figure being addressed. And it knows what the figure is based on the type system. In this case, it knows that it's pointing to an int. That's why those are 4 bytes. That's why all these rectangles are seemingly 4 bytes wide. In this example up here, ampersand of pi evaluates to fraction star. So when I start treating it like it's an array, even though it's not, it has no choice but to rely on this rule right here to figure out where the 1th, counting from 0, fraction would be, starting at this address. Okay, and that's why it advanced 8 bytes beyond the base of that entire drawing to figure out where to start dealing with things. Okay, does that sit well with everybody? Yes? Yep.
Is there any way to get access memory that isn't the size of your...
There is. You can actually use some casting tricks. I'll do that in a second. Okay, I will do that probably in 2 or 3 minutes, but I'll do a really good example for that question. Okay, what I hope is a good example. I should say it that way.
Question for the array of the index -4.
Right.
So the indices 0 through 9 are yours.
That's correct.
Everything outside might.
That is correct. So just because I write a 1 here and I have code that actually tries to do it, doesn't mean that while it's running it's going to succeed. If it succeeds, it does place the bit pattern for 1 there. It might also crash, okay? Or it might actually succeed, but this space right here, we'll see this very shortly, this space right here and this space right here is going to be associated with other local variables that happen to be declared above this and below this. There's no impact here because this is the only declaration. But if I were to declare int I right there and double D right there, the model we're going to use, and this is the model that's really used, is that it packs all local variables into a little thing called an activation record. That's just fancy terminology for the block of memory that's set aside for all local variables in a function. So if you touch this right here, you're really touching some other local variable. You're touching the one over here that was declared after the array. That's just the way it kind of works out. Okay? Does that make sense? Okay, there's a couple of more rules I want to talk about here. When you dereference, this right here if you put an asterisk in front of this ampersand right here, they kind of negate one another. So this is synonymous with array of 0. The extension of that for this line is that if I put an asterisk in front of this, the pointer arithmetic is done first, so it computes the address of the integer you're interested in, and then the asterisk actually brings you into that rectangle. It is synonymous with that right there. So that's why when you do something like array of -4, you're really doing this. Whoops. Pointer arithmetic brings you not 4 bytes before, but 16 bytes before that address. You dereference it to actually sit in and find yourself in the rectangle that's capable of receiving the 77. Does that make sense to everybody? Okay, that's great. So in a second, I will start mixing arrays and structs. But to get to your point with regard to how do you access the internals if you want to do it, you rarely want to do it, although there are actually, it turns out that there are features of assignment 2 that rely on this type of knowledge. I'm not encouraging you to write this code, but I don't see the disadvantage of understanding it. If I go ahead and declare, let's say, an int array, I'll keep it small, 5. Whoops. I get this right here, 1, 2, 3, 4. If I go ahead and set array of 3 equal to, let me do 128. Uninitialized, left uninitialized, left uninitialized, left uninitialized. I actually put a 128 there, and I'm drawing it in the right half of the box because that's really where the bits will be updated. Everything to the left of the 128, right here, will be all zeros, and this will be 1 followed by 7 zeros. I'm just emphasizing the fact that the 128 happens to fit in the lower of the 2 bytes. Okay? If I do this, the data type of that is int star, right? Unless I do this. Okay, now ARR is brainwashed momentarily into thinking that it addresses a short, and there incidentally is space for 10 shorts there. Okay? The way ARR, or the way the result of that expression sees it, that's short of 0, that's short of 1, short of 2, short of 3, short of 4, short of 5, short of 6. Make sense? Okay? This is kind of what you were getting at, I'm assuming. 0, 1, 0, 2, 4, 6. It's going to write a 2 in that byte right there. Okay? So when I go ahead and I see out less than ARR of 3 less than ENDL, you are not printing out a 128. You're actually printing out 512 plus 128. Everyone know where I'm recovering that 512 value from? Okay? If this is the number 2 and I multiply it by 2 8 times to get it into that position right there, that's really 2 to the 9th plus 2 to the 7th. Okay? And so it's going to print out whatever that number is right here. Okay? I can go arbitrarily nuts with all of this casting. If I want to set ARR of 1 address, and I want to cast that to be a car star, I want to add 8 to that, and I want to cast that to be a short star, and I want to find the third short after that and set it equal to 100. I think I have the patience to go through with this and show you what's going on right here. ARR of 1 is that box right there, so the ampersand is that right there. Pretend just for me that you're a car star so I can do something funky and add 8 to you, but have it mean 8 times size of car, plus 2, plus 4, plus 6, plus 8. So that's the address of this right here. Okay? You're a car star, no you're not, you're a short star. Okay? Pretend you're the base address of an array. I don't care how long of an array it is. Just go 3 shorts forward of that short star that's right there to figure out where to write a 100. This is the 0th one, this is the 1th one, the 2th one, the 3rd one. this is where the 100 would go. Okay? Don't write code like this. Just understand it. Okay? This makes sense to people now? Okay. Let me start blending structs and fractions to get more interesting examples. Come Wednesday, we're going to be able to do meaningful stuff with this knowledge. Right now, it's all gibberish and seems like it's just contrived code. It is certainly contrived code because the examples need to be small and focused. But once we understand how to deal with memory, and that's what we're really doing with all of these examples, you'll be able to take that understanding of memory and write meaningful generic code in C. C, we don't have templates. That's how we dealt with generics in C++. In C, we have to leverage over the fact that we know the size of everything and we know that bit patterns represent values to be able to write a generic binary search or a generic linear search or a generic swap function or a generic vector or things like that. Okay, and that's what Wednesday and Friday and probably next Monday are going to be all about. Did you get this example? Okay. If you don't get it yet, the section handout come next Tuesday, not tomorrow. We'll deal with more of this stuff. Okay. Let me go on to structs with arrays inside of them. I'm going to need 2 boards. That's why I'm erasing so much. I should just erase with the chalk. Here's the struct definition I want to deal with. Struct student. Okay. I have a field inside. I want to store an exposed character pointer. You're not used to doing this because you had a string class in C++. We actually don't have those in pure C. They're always represented as character arrays, okay, where the characters in the string are laid out side by side. Rather than there being a period at the end, there's what's called the null character, the \0 character that's at the end. This one's going to happen to reside as a string outside the struct. All I want to do is I want to store the address of the 0th character of the entire name. That's different from this. SUID of 8. I want to store the individual digits of a 7-digit SUID in an array that's wedged inside the struct. This will become clear from a picture in a second. And then at the bottom, I just want a normal old integer, num units. And there we have our definition. Okay. What's a picture of one of these things look like? It looks like this right here. There's my car star. There's my static character array of length 8. And there's my num units field. So this is a 16-byte struct. Okay. You're not used to looking at these things this way, but in memory diagrams, at least for the next day, you read left to right, bottom to top, because you're always worried with lower addresses. The address of the entire struct is coincident with the address of that car star. Okay, so to see this arrow, you don't actually know whether or not it's a student star or a car star star. Yes, we will be dealing with double pointers. Okay. If I go ahead and declare 4 of these things in an array, student pupils of 4, then I get 4 of those things laid out side by side. The way of laying down the elements, the base elements of an array, is the same whether you're dealing with booleans or ints or doubles or structs. So actually I'm going to have 4 of these things. Draw those right there to make it clear that that's the 0th, the 1th, the 2th, the 3rd. Okay. So I have all 64 bytes of memory for my packed array of 4 items. Each item is a struct, and the same skeleton or the same view of memory overlays each of those 4 quantum elements. So when I do this, pupils of 0.num units equals 21. You know that 21 goes somewhere, and this isn't too bad. You know it's going to go in the space that's dedicated to the num units field of the very first student struct. Okay? If I do this, pupils of 2 dot, let's say name, is equal to, there's this function I want to talk about, stirdup. Adam. STRDUP, stirdup, it's actually a shorthand for string duplicate. Okay, so what this does as a function is it dynamically allocates just enough space to store the string, in this case Adam, and then it actually writes down Adam in that space, and as a function returns the address of the capital A. Okay? These 4 things right here are all local variables. I'm sorry, the entire array is a local variable. It resides in a part of memory called the stack. I'm assuming you've heard of the word stack before. You may not have heard it talked about in the case of memory. But the dynamically allocated string, and this is dynamically allocated, that is drawn from a part of memory called the heap. Logically, we assume that it's 5 bytes. It actually makes space for that \0. Okay? And then the address of that new figure right there, after it's been initialized with whatever this string logically is, gets returned, and it's dropped in the name field of the third counting from 0, okay, struct. So this gets placed right there. Okay? That's very different than this type of setup, where pupils of 3 dot name is equal to pupils of 0 dot suid plus, let's say, plus 6. There's a lot going on that line. Let's just look at the right-hand side. Pupils of 0 dot suid. Pupils of 0 suid of 0 is that right there. Pupils suid of 4 is right there, but I don't have any array index dereference going on there. I have just the raw array name right there. That's synonymous with that arrow right there. In spite of the fact that this is a big nasty expression that evaluates to a pointer, when I add 6 to it, it's doing pointer arithmetic against a car star. Okay? So the 6 is effectively, even though it doesn't matter, it's scaled by the size of a character, which is 1. And so the overall right-hand side expression is the address of that character right there. Does that make sense to people? Okay. The tail of that arrow is assigned right there. All I did was I assigned an actual value to the name field of the very last student in that record. It happens to be the address of something that resides inside the entire figure. Okay? If I do this, pupils of 1, oops, messed up. str, not dupe, cpy of pupils of 1 dot suid 40415xx right there. Stir copy is like stir dupe, except it doesn't actually allocate any memory. It assumes the address where you should copy the string is identified via the first argument. So what this does is, beneath the surface, in stirdup as well, but specifically in stir copy, there's some little for loop that keeps on copying characters one after another until it finds a \0 and it copies that as well. In fact, stirdup, after it calls C's equivalent of operator new, which is called malloc, it actually calls stir copy. This right here, in this 1-by-1 basis, would write a 4 right there, and then a 0, and then a 4, and then a 1, a 5, an X, and a \0 would be written right there, and then it would return. And it's completely useful because of its side effect of copying characters around. You have to make sure that the address you pass in there actually points to character space that's really under your jurisdiction, because it's going to try and write characters to whatever address is specified there. You better make sure it's a good address. Okay? This one right here, stir copy again, of pupils of 3 dot name 1, 2, 3, 4, 5, 6, and that's enough. Don't worry about the fact that it's not really a Stanford ID. It was 70 years ago, I'm sure. Pupils of 3, dot name. That evaluates to whatever this evaluates to. That means that location right there, okay, is what's identified as the place where characters should be written, okay? It follows exactly the same recipe that the first call to stir copy did. It's not as if this byte and this byte are auto-decorated behind the scenes as things that can only store characters. And it's not as if that's turned off right here. As far as stir copy is concerned, it sees this as a base address of an arbitrarily long character sequence space where characters can be written. And so what's going to happen is it's going to write the digit character 1 right there. It's going to write the digit character 2 right there. It's going to do exactly the same thing right there with a 3, a 4, a 5, and a 6. It's going to write a \0, whoops, not there, in the leftmost byte of that name field right there. Okay, does that make sense? And then stir copy is like, I did my job. I'm awesome. I'm going to return back to the main function. So when you come back, if you want to print out the number of units the student is taking, it's a lot. Okay, it is 3 times 2 to the 24th plus 4 times 2 to the 16th plus 5 times 2 to the 8th plus 6. They'd have to petition to do that. Okay, if I go ahead and I print out this string right here and I actually pass this in, if I do cout less than pupils of 3 dot name, it actually would print 1, 2, 3, 4, 5, 6, and that's it. Okay? That's because it just receives the address of something it trusts to be a character, followed by probably another one, followed by yet another one. It just crawls over consecutive bytes in memory until it incidentally finds one with a 0 in it. Does that make sense to everybody? Okay. Again, you will not be writing code like this, okay, but you should be able to understand, at least believe that the drawing that I'm putting here is consistent with the code. You had a question? Yeah, pupils 3 dot name. So this right here, the name field, it's not ampersand of name. So I don't pass the address of this box. I have pupil of 3 dot name evaluate itself. Okay, so this is the number 1000 in here. It's because the address of that box right there is really a 1000, and that's what's passed to stir copy. So it starts copying characters to address 1000, and then 1001 and 1002, etc. Does that make sense? Okay. Question in the back? No. Okay. You guys are good? One other thing. Yep, right there.
The local variable, sorry. What happens?
If I this right here, before this block ends, unless I want to pretend that like Adam is a helium balloon and I want it to fly off and never be recovered, I would have to free it before this code block. And I could just do that by passing pupils of 2 dot name to free. Okay, free is the C equivalent of this delete thing you're familiar with. Okay. Nope, not at all. That's Java. That's not C++. Okay, one other line. Pupils of 7 dot SUID of 12. Let's not do that. Let's do 11. Is equal to the character A. Just because there are structs involved doesn't mean it intimidates the executable. It will go ahead and it will do the manual point arithmetic to find out where the 7th student would reside if this address, if the array actually existed there. So I would go to not the 0th, the 1th, 2nd, or 3rd. I better go to the 4th, the 5th, the 6th, the 7th. There's a gesture, a little phantom halo around the space that we're identifying or pretending is pupils of 7. Then I jump to its SUID field. That would reside and begin right here, as if I legitimately had space for 8 characters right there. It even double whammies the system and goes beyond that array boundary. This is 4, I'm sorry, this is 0, this is 4, this is 8, 9, 10, 11. It would write this scattered A, 65, in that one little byte over there in memory. Would it succeed while it's running? If it crashes, no. If it doesn't, yes. Okay, that's just the way it will work out. Okay, does that make sense to people? Okay. If I were to go ahead and I were to print in this state right here, if I were to print just the address itself, all I know is that the other 3 bytes are uninitialized. If I print this entire number, okay, all I can tell is that it would be less than 2 to the 24th. That's all I know. Because I zeroed out the really large contribution to the overall thing. Does that make sense? Okay. If I were to print out this right there, if I were to pass that car star, it has no idea that it's the address of a character that happens to be in a larger string that starts before it. So if I were to pass that address to cout less than, it would print 1xx, and that's it. Does that make sense? Okay, just to make that clear to everybody. No boards. Here is, let's just say it's a dynamically allocated string that has Colleen \0 in it. Okay? If I pass that address to cout, it prints out the entire name Colleen. If I use my pointer tricks to pass that to cout less than, it still begins a null terminated string. It happens to not mean as much to us, but it'll still print it out textually. It would print out LLEEN. Okay? If I pass that right there, it would print out EN. If I passed that, it would just print nothing, because it doesn't actually print the \0. So that's basically this weird representation of the empty string. Okay? Does that make sense to people? Okay. Very good. Okay, you guys are doing okay? Good. What I want to do now is I want to start talking about how to write generics in C. We have enough experience with this memory business so that I can actually write a real function in C that leverages off of this stuff. Let me just write a function I know you've seen before, and it's actually charmingly simple for us to go out. This is all very difficult compared to what I'm about to write. Actually, this board's better. I want to just write a really simple function and use advanced memory terminology to describe what happens. Void swap int star. Actually, you probably haven't seen this version before. You've used references in the past. What happens is that you probably declared 2 integers, x, 7, int y is equal to 117. And I'm concerned with the call to swap where I pass in the locations of my x and y variables. C, and I'm writing a pure C function right here, has no templates. That's relevant. It also has no references. Okay, so there are fewer meanings of the ampersand symbol in C. What I'm doing here is I'm assuming I own x and y as little jewel boxes, and I pass the addresses of those to this swap function, so it knows at least where to go to move byte patterns around. And that's effectively what's done by the swap when you think about it in memory terms. Okay, does that make sense? So this is a function I haven't written yet, but I know that this thing called AP and BP, the P is there for, just to remind myself that it's a pointer. This points to the X box and the Y box that has a 117 in it. So what I want to do is I want to exchange the 7 and the 17. The way I do this is I declare a temp variable and set it equal to what I get by traveling from the AP pointer to the space it addresses. So I get temp right there. How is it initialized? It's not set to this number. The asterisk says, please hop forward once to find the place that should be copied. The bit pattern for that 7 is replicated right there, but because temp and the space addressed by AP are both ints, the bit patterns mean the same thing in both contexts. Then I do this. A little bit more involved, but you understand certainly what's going to happen. You may not, if I wrote a more difficult version of this type of function, it might not get it, but what happens here is the space addressed by AP, not this space right here, but the space addressed by it, is identified as the L value, or the recipient of whatever the right-hand side evaluates to. The right-hand side evaluates not to BP, but to what it addresses. Okay? So this 117 is replicated right there. The 4-byte representation of 117 is replicated in the space addressed by AP, And then finally, I do this. BP addresses whatever was stored here previously, and that's how I get a 7 right there. Let's get a better 7. Okay. Now, what I did there algorithmically had very little to do with ints. The only part of the fact that the only fact about ints that was involved was that the figures being rotated and swapped were 4 bytes. Okay. Make x and y floats. Make this float star and make that a float. The pictures can even stay the same in terms of the drawings, in terms of the sizes. They're still 4 bytes, and as long as I exchange all of these things, okay, then I'm going to effectively achieve the swap, even though I don't necessarily care that they were floats versus integers. Okay? If I pass in double stars or car stars or bool stars or struct student stars, the same rules apply. Okay? It's bit pattern swapping is what it really is. Okay? You know enough about generics from CS106B and 106X to know that we would probably use references, because references are prettier, right, from this point forward. And we would also templatize it if we wanted the same block of code that we write to be used in different type scenarios. We have neither one of those in pure C, but there are several situations where you do benefit by actually going the extra mile and making the code you write generic. Okay? Well, it's not pretty. Turns out it's actually it's something of a hack to write a generic function in C, but it is the way it's done. And once you understand memory really well, you stop thinking of it as a hack and you start to see it as very, very beautiful, okay, as the way it actually works, because you understand what's happening on your behalf when you swap these two figures and you just specify the addresses. Or you linear search this array. And the algorithm for linear search is the same whether or not ints or strings or struct students are involved. Binary search the same way. Merge sort, quick sort, all of those things you learned about and templatized in 106B still can be done in languages older than C++, using this information about memory that we've learned over the last 2 lectures. Okay? So come Wednesday, I will go generic on you with this function right here and frame it in terms of generic pointers and generic byte swappers. Okay? Have a good night.